Hello viewers, welcome to Elimu TV. Wainoga Jen is your teacher today. And I want for all those who are together with me in this lesson, I want you to SMS me with the number 21126 so that we can communicate with you through the number. So in our Form 2 work, in our previous lesson, I left you with an assignment. The assignment that we had was under the topic relative atomic mass. Relative atomic mass and isotopes. Under this topic, in our previous lesson, I taught you how to calculate the relative atomic mass of a particular element, and I left you with an example question as an assignment to simply try and see whether you are in a position to calculate the relative atomic mass. So the question was that one naturally occurring gallium consists of the isotopes gallium 69 and gallium 71 in the ratio 3:2, and you are supposed to calculate the relative atomic mass of the gallium element. So from there then, how are we supposed to have done that calculation? So as we had said in our previous lesson, we always start this question answering by writing down the formula of our equation, that is the relative atomic mass is equals to the average mass of an element, over, we said, the half mass of the carbon 12. Therefore, our gallium isotope, as it was appearing, our gallium isotope had a mass of 69 and the other one had a mass of 71. And therefore, there were two of them in the ratio of 3:1, and to calculate the relative atomic mass of it, we are supposed to take the mass number of the first isotope of gallium, and that is the 69. We multiply by the ratio, that is 3. We put that in brackets and add the other mass of the gallium element, that is 71. We multiply by the ratio, which is the 2 there. And then we are going to divide that by the total ratio of the elements that we have, that is 3 plus 2. Therefore, the 3 plus 2. Therefore, the 69 multiplied by 3, we get a total of 207 plus 71 multiplied by 2 is 142. We divide by 3 plus 2, we get it is 5, and our answer is going to be 69.8. The 69.8 that we have gotten there is simply the total, or it is the relative atomic mass of our elements. So it is not going to be the mass of the gallium elements that we have appearing as our isotopes. That B69.9 will be the relative atomic mass of our two isotopes. I would wish to also give you another example that is mainly involving figures that are in percentages, and we see how can we apply that also. So I have our example 3. I had given you example 1, that was example 2. We have example 3. In our example 3, it reads, an element that we are going to call X consists of 3 isotopes. It consists of 3 isotopes with a mass number of 22, 24, and 25, with an abundance of 89.6% for the first mass, 6.4%, and 4.0% respectively. And the question is now, find the relative atomic mass, of element X that we are given above. So from this question, we have the way this element X appears in their various isotopes: an isotope of 22, an isotope of 24, and an isotope of 25. But all of them have a percentage abundance of 89.6, that stands for the 22. The 6.4 comes or stands in for the 24, and the 4.0 stands for the 25. So having that in our mind, how do we now calculate the relative atomic mass of those elements, or that element that we are calling our element X? Once again, we have said we always begin with writing the RAM, that is relative atomic mass, which is equals to the average mass of the element, and we divide that by half the mass of a carbon atom, that is the carbon 12, which we have there. Therefore, our average masses, we have them as given in the question. That is, we have the 89.6, we multiply by the first percentage, and the first percentage was 22. No, the first mass was 22, sorry, when the percentage, that is 89.6. The second one was plus, the second one, the mass was 24. We multiply by the percentage, that is 6 times 4. And we add to the other average mass, and that was 4.0. We multiply by the mass, which was 25. So if we add all of them together, because the masses were in percentage, we are then going to divide our average mass of our element by 100, the figure 100 there. Therefore, the total masses that we have are going to give us an answer of 22.2. So the answer that we have here is simply the relative atomic mass of our element X that we were calculating for, but not the mass of our element X. So it is the relative atomic mass. Remember what we said in the previous lesson, that the atom is usually a very small element or a very small particle of an element, and therefore its weight cannot be picked, its weight cannot be taken, or we are not able to get its weight. Therefore we have to relate its weight to the mass of another standard element, and we said our main standard element will now remain the carbon element. So that is all for the calculation of the relative atomic mass of an element. From there, now that we have known how to calculate the relative atomic mass of an element, I want us to go to something new which we call electron energy levels in an atom. The electron energy levels in an atom. So in our previous lessons, or the very first lesson that we learned in the Form 2 work, I can remind you of what we learned about. We drew the structure of an atom. The structure of an atom simply consisted of one, the nucleus, and the nucleus was occupying the innermost part of our atom. The nucleus had the subatomic particles, that was, it consisted of the protons. The protons, we denoted them as a small p, and the neutrons, which we also denoted as a small n. Outside the nucleus, we said that we have some shells, and the shells that we had, we drew them like that. So these are the shells in an atom, and this is the nucleus in an atom. We said that an atom consists of three subatomic particles. We talked of it consisting of the protons, it consists of the electrons, and it consists of the neutrons. The protons and the neutrons, we said they occupy the nucleus. The electrons that we have here, we said that they occupy the energy shells. Therefore, where do they occupy then? So our electrons will always occupy the energy shells at that point. Therefore, from there, from our topic, electron energy levels arrangement in an atom, how are we going to go about that? Therefore, we want to see where do we place our electrons. Before we go further into the details of drawing the structure of an atom indicating the energy levels, I want to remind you of what an electron was. An electron was first the negatively charged particle in an atom which had a mass of 1, and it was simply found on the shells. From there, we need to know again now that the electrons simply dictate the property of an element. How does it dictate the property of an element? It is usually occupying the shells, and the position at which it occupies on the shell, and also the different number of electrons that are occupying the atom depends, or they determine mainly the way an element is going to behave. So the characteristic or the properties of an element or an atom can be determined mainly by the electrons, and the electrons occupy the outermost part of an atom. Therefore, if we are to start on the atom and show how the electrons arrange themselves on an atom, I can have, once again, the nucleus of our atom, and outside the nucleus of our atom, the first circle that we have there is what we are calling the shell. The first shell in an atom always is occupied by the electrons. I can decide to use the cross sign to represent my electrons. And therefore, if this is the nucleus, these are the shells, then let's see how is the arrangement of those elements. The first energy level, the shells, we also call them the energy levels. So the first energy level, or what we are calling the shell, is always occupied by a total number of 2 electrons. Therefore, it can be occupied by a lesser number than 2, e.g., we can talk of it can be occupied by 1 electron, but the maximum number of electrons that this energy level, the first energy level that it can hold, is simply a maximum of 2. The second energy level, or the second shell, is always occupied by a maximum number of 8 electrons. It is always occupied by 8 or less, but not anything above or more than the 8. The third energy level also is always occupied by a total number of 8 electrons. It can be occupied by less, but not more than the 8. The fourth energy level also is always occupied by the 8 electrons, but nothing more than the 8, but can be occupied by less than 8 electrons, sorry. Therefore, for the first energy level that we have said that the first energy level is always found very close to the nucleus. So if this is the nucleus, the first energy level is there. Remember, we are saying that the energy level is first of all occupied by an electron. We said there previously that the nucleus consists of protons. And we said that the protons are always positively charged, while the electrons are always negatively charged. Therefore, there is always a very strong force of attraction that exists between the nucleus and the electrons that are occupying the energy levels. Therefore, we can say that the energy level to the outside, or this first energy level, has a very close connection or a very close attraction force that exists between the protons in the nucleus and the electrons that are found on the energy shells. As we remember the fact that we usually have in science that always the negative charges will always attract while the similar charges will always repel. So we have the positive and the negative, therefore they attract each other. As we move on the atom, having the other shells or the energy levels, then the attraction force between the outermost energy level electrons to the protons then go descending or extending. It becomes weaker as we continue increasing our atomic structure. Therefore, that force of attraction between the protons there and the electrons there, if our atom is that large, then it becomes less. This attraction force between the first energy level and the nucleus there, then is much, much more stronger. So from there, we are going to give an example of a number of atoms that will help us to know exactly how do we draw the structure of an atom. For example, I may have a hydrogen atom. A hydrogen atom has an atomic number of 1. Therefore, the hydrogen atom, if I am going to draw it in the atomic structure and show the energy levels in it, I am going to have my nucleus there. In the nucleus, I will have the proton number being 1. I will have the neutron numbers also. And I will have the energy shell that we have there, or the energy level. So the energy level, because the hydrogen has an atomic number of 1, then I'm going to show my electron appearing there as 1. Therefore, from what now we have learned, I just want to remind you of what we learned even previously, that always the atomic number is always equals to the number of protons and is always equals to the number of electrons. Therefore, if we give the atomic number of an element like the hydrogen I'm giving of 1, then it means the number of protons is 1 and the number of electrons is 1. In our lesson, we have just learned how to draw the energy shells around the nucleus of an atom. We have seen how we can arrange the energy levels in an atomic structure. And therefore, from what we have learned today, we are going to have a number of more examples in our next lessons where we will see how we can draw other atoms showing the energy shells. Therefore, I will see you in our next lesson. But before we wind up, I want to remind you of our fingertips line, whereby in our fingertip line, I want you to send a message on CHEM, standing for chemistry. This is form 2 work, therefore you write 2, CHEM2, and you SMS to number 21126. Goodbye. See you in the next lesson.